In this video, we're going to be looking at some numbers with mass and weight and how they can be calculated from one another. Let's start with this. Mass and weight are related. So a 1 kilogram bag of dog food has a weight of 2.2 pounds on Earth. A 2 kilogram bag of dog food has a weight of about 4.4 pounds. All right, so it's a pretty simple relationship. Well, in physics, instead of using pounds, scientists use a different unit for weight. And the purpose of this unit is to actually make things easier, surprisingly enough. But it may not be apparent how it's actually easier yet. So just trust me. But instead of using pounds, scientists use a unit called a Newton, named after Isaac Newton, of course. So a 1 kilogram bag of dog food has a weight of about 10 newtons. And a 2 kilogram bag of dog food has a weight of about 20 newtons. And just so you know, a force of 1 newton is about the same as the weight of an apple. So an apple weighs about 1 newton, maybe a little bit more, but a small apple has a weight of about 1 newton. And I'm about done with apples at this point. So let's look at some examples of an equation that shows this relationship with some numbers in it now. Okay, so what we just saw there is represented using this equation. An equation in physics is just a way of saying something. Instead of using words, we use symbols. So an equation that shows the relationship is weight is equal to the mass of an object multiplied by 9.81 newtons per kilogram. And this number is one that we've just experimentally measured on Earth to show the connection between mass and weight. This is only true for Earth. So on the moon, it's a different number. On Mars, it's a different number again. But this 9.81 is how many newtons something weighs for every kilogram of mass it has. So newtons per kilogram, there's 9.81 newtons per kilogram of mass on Earth. Now, this number, 9.81, is actually the same as 9.81 meters per second squared, or meters per second per second. And as we'll see later, this is actually the acceleration that an object experiences when it falls freely on the Earth. What that means is every second that passes, an object will gain its speed by 9.81 meters per second. So this is how quickly an object speeds up as it falls to the Earth. And that's related to the weight of an object, how much force is being pulled down on that object. So another way of saying this, and this is the way that it's most commonly represented in physics, is that the weight of an object is its mass times the acceleration due to gravity on whatever planet you're on. And we're going to assume it's always Earth unless it's otherwise specified, but the acceleration due to gravity on Earth is 9.81 meters per second squared. So now is where it gets a little potentially confusing. We're going to take away these words and we're just going to put in symbols. And unfortunately, there's not really a good symbol for weight in physics. There's no W. W is already used for things like watts. And so instead of using a W for weight, they use a capital F for force, because weight is a pulling force. And it's a specific kind of pulling force. It's the pulling force due to gravity. So they use a little g, a subscript g here. So the force due to gravity is the same thing as the weight. And so there's a translation that happens here. You got to translate this in your mind. You can read this as the force due to gravity, or you can translate it as weight. So the weight of an object is equal to the mass, little m, times g, little g, is the acceleration due to gravity. And here are those equations written a little bit simpler and shorter. So that is the connection between mass and weight. So let's look at some example problems before ending this video. 3 problems that are quick and easy. Let's start with the weight of a can of Diet Pepsi. So let's say we have a 0.35 kilogram can of Diet Pepsi. What is its weight? So the weight, again, is mass times the acceleration due to gravity. So the mass, we substitute in 0.35 kilograms. Acceleration due to gravity is 9.81 newtons per kilogram. Multiply those two together, and we get 3.4. And notice how the units here cancel each other out. We have kilograms and then newtons per kilogram. You multiply those units together, and they cancel each other out. We're left with newtons as our answer. So 3.4 newtons is the weight. What about the mass of a 1,500 newton sofa? So I've got a heavy couch here. What's the mass of that couch? Well, now it's a little different because we're solving for the mass. We're still going to use the same equation. We set it up like this. The weight is equal to the mass times g. We put in for the weight 1,500 newtons. Leave the mass. G is 9.81 newtons per kilogram. Now, we need to solve for mass, and so we're going to use some algebra skills here. Right now, to solve for mass, we need to isolate it. We need to get it by itself on one side of the equation so we can say what it's equal to on the other side. To do that, we need to undo whatever math operations are happening here. So right now, it's being multiplied by 9.81. We need to undo that so we can get rid of this whole chunk over here. So to undo multiplication, we do the opposite. We divide. And so I'm going to represent division here with a fraction. I'm going to divide by 9.81 newtons per kilogram on both sides. Oh, sorry, it's kind of awkward to write at this angle. Okay, so we do that. Divide, we've undone this part over here, so it's just all completely gone now. We're left with the mass. And then we do this in a calculator, 1,500 divided by 9.81, and that gives us 153. Now here, the newtons end up canceling out, and we're left with kilograms for our mass. So that is our answer. You can write it like this, 153 kilograms equals the mass, but I find it's easier to translate into English if we just swap those two, which you can do. They're equal to each other either way. So I like to write it with the variable at the beginning because then it's easier to read. Mass equals 153 kilograms. So I like to write it like that. It doesn't matter either way. All right, then finally over here, we have the weight of that same sofa over here. But let's say the sofa was on the moon. And on the moon, the acceleration due to gravity is 1.6 meters per second squared. So same equation as before, but this time instead of 9.8, we're going to put in 1.6. So we do the mass, which we just found over here, 153 kilograms, times 1.6 meters per second squared. We do the math there. That's 245 kilograms times meters per second squared for our units. These units being multiplied together like this, it looks like a mess. These two units, or these three units all put together, is actually the definition of a Newton. And so we write that down here. We'll talk more about this later on in our course, but this is the same as a Newton. And so our answer is that this couch weighs 245 newtons on the moon. That's a lot different than 1,500 newtons on the Earth. It's a lot lighter on the moon. So that's all I've got for you for this video. Remember, how you do anything is how you do everything.